Here is today's problem. We are given two separate mathematical statements to work with. The first statement is the linear equation x plus y equals 12. The second statement is the nonlinear equation x times y equals 36. Our goal is to find real numerical values for the variables x and y. These values must satisfy both of the given equations simultaneously. We will begin our algebraic process by focusing on the first equation. The first equation relates our two unknown variables through addition. It states that the sum of the variable x and the variable y is 12. To proceed, we want to isolate one of these variables on a single side. Let us choose to isolate the variable y on the left side of the equals. Currently, the variable y has the variable x added to it on the left. To undo this addition, we must subtract the variable x from both sides. On the left side, the positive x and the subtracted x will cancel out. This cancellation leaves the variable y completely by itself. On the right side, we start with the original constant value of 12. We then subtract the variable x from this constant value of 12. This operation gives us a new algebraic expression of 12 minus x. So we have established that y is equivalent to 12 minus x. This newly formed equation will be very important for our next steps. We will now turn our attention to the second equation in our system. This equation states that the product of x and y equals 36. It contains both of the unknown variables multiplied together. However, we just found a way to express y strictly in terms of x. We determined that y holds the same numerical value as 12 minus x. We can use this equivalence to perform an algebraic substitution. Everywhere we see the variable y in the second equation, we replace it. We will substitute the expression 12 minus x in place of y. Let us write out what this substituted equation looks like on paper. We start with the variable x on the outside of a set of parentheses. Inside the parentheses, we write our substituted expression 12 minus x. We close the parentheses to show that x multiplies the entire quantity. This entire product is then set equal to the number 36. We have now successfully created an equation with only the variable x. This single variable equation is something we can solve directly. Our first task in solving this is to expand the mathematical expression. We must use the distributive property of multiplication over addition. The variable x outside the parentheses must multiply every term inside. We will perform these two multiplication operations one at a time. First, we multiply the outside variable x by the first inside term. The first term inside the parentheses is the positive constant 12. Multiplying the variable x by 12 gives us the term 12x. Next, we multiply the outside variable x by the second inside term. The second term inside the parentheses is negative x. We must be very careful with our positive and negative signs here. Multiplying a positive x by a negative x results in a negative product. Specifically, x times negative x evaluates to negative x squared. We have now finished distributing the variable across both inner terms. The left side of our equation has expanded into 12x minus x squared. The right side of our equation remains unchanged as 36. Let us write down this newly expanded equation in its complete form. We have 12x minus x squared equals 36. This mathematical structure is known as a quadratic equation. It is called quadratic because the highest power of the variable is 2. To solve quadratic equations, it is best to write them in standard form. Standard form requires all terms gathered on one side of the equals sign. The opposite side of the equation must be left perfectly equal to 0. It is also common practice to make the squared term positive if possible. Currently, our squared term on the left side has a negative coefficient. To fix this, we move all the terms from the left side to the right side. We will move the negative x squared term first by using addition. We add positive x squared to both sides of our current equation. On the left side, the negative and positive x squared terms sum to 0. On the right side, the positive x squared term simply appears. Our equation now reads 12x equals 36 plus x squared. Next, we need to move the 12x term to the right side as well. Since it is positive 12x on the left, we must subtract it. We subtract 12x from both sides of the equals sign. On the left side, 12x minus 12x leaves us with exactly 0. The right side now contains three separate mathematical terms. The terms are 36, positive x squared, and negative 12x. Let us write the complete equation with all these newly arranged terms. 0 is equal to 36 plus x squared minus 12x. By convention, polynomials are written in descending order of exponents. We will rearrange the terms on the right side to follow this convention. The term with the highest exponent is the positive x squared. We will place this squared term at the very beginning of the expression. The term with the next highest exponent is the negative 12x. We will place this linear term in the middle of our expression. The constant term of positive 36 goes at the very end. Our correctly ordered equation is 0 equals x squared minus 12x plus 36. We can symmetrically flip this equation to read from left to right. This gives x squared minus 12x plus 36 equals 0. We are now ready to apply the quadratic formula to find the roots. The quadratic formula requires us to identify three specific coefficients. Let us define three uppercase variables to represent these values. We will use the uppercase letters c, d, and e for our coefficients. Let the variable c represent the coefficient of the squared term. In our equation, the x squared term has an implied coefficient of 1. Therefore, our variable c is assigned the numerical value of 1. Let the variable d represent the coefficient of the linear term. The linear term in our equation is negative 12 multiplied by x. Therefore, our variable d is assigned the numerical value of negative 12. Let the variable e represent the constant term in our quadratic equation. The constant term without any variable attached is positive 36. Therefore, our variable e is assigned the numerical value of 36. We will first calculate the discriminant portion of the quadratic formula. Let us define a new uppercase variable k to store the discriminant value. The formula for k is d squared minus 4 multiplied by c multiplied by e. We will evaluate this discriminant expression one piece at a time. First, we need to calculate the squared value of our variable d. This means we must multiply negative 12 by another negative 12. A negative number multiplied by a negative number yields a positive result. 12 multiplied by 12 gives us 144. So the value of d squared is positive 144. Next, we calculate the product of 4, our variable c, and our variable e. Our variable c is 1, so 4 multiplied by 1 remains as 4. Then we must multiply this 4 by our variable e, which is 36. Let us break down the multiplication of 4 and 36. 4 multiplied by 30 gives us exactly 120. 4 multiplied by 6 gives us exactly 24. Adding 120 to 24 gives 144. So the subtracted part of our discriminant is also 144. Now we subtract this second product from our initially squared value of d. We are subtracting 144 from 144. Any number subtracted from itself leaves a remainder of exactly 0. Therefore, our discriminant variable k is perfectly equal to 0. The value of the discriminant tells us about the nature of our solutions. A discriminant of 0 means there is only one unique real solution. We can now plug this discriminant back into the full quadratic formula. The formula tells us that x equals negative d plus or minus the square root of k. This entire numerator is then divided by the denominator of t times c. Let us start by evaluating the first part of the numerator, which is negative d. Since d is negative 12, taking the negative of it makes it positive 12. Next, we must take the square root of our discriminant variable k. We calculated earlier that the value of k is precisely 0. Usually, taking a square root involves considering a positive and negative branch. However, the square root of 0 is just 0, collapsing both cases into 1. So the plus or minus the square root of k simply becomes plus or minus 0. Adding 0 or subtracting 0 from 12 will yield the same result of 12. Our complete numerator therefore simplifies down to exactly 12. Now we will evaluate the denominator of the quadratic formula. The denominator is 2 multiplied by our coefficient variable c. Since c is equal to 1, we multiply 2 by 1 to get 2. Our complete denominator simplifies down to exactly 2. We find the final value of x by dividing the numerator by the denominator. We must divide the number 12 by the number 2. 12 divided by 2 gives us a final quotient of 6. We have now rigorously proven that the variable x must be equal to 6. However, our task is not fully complete just yet. We still need to determine the correct numerical value for the variable y. To do this, we can return to the first isolated equation we created. Recall that we established y is equal to 12 minus the variable x. We now have a concrete numerical value to substitute for the variable x. We will replace the letter x in this expression with the number 6. This transforms our equation into y equals 12 minus 6. Performing this simple subtraction is straightforward arithmetic. 12 minus 6 evaluates to precisely the number 6. Therefore, we have determined that the variable y is also equal to 6. Our final solution set is the pair where x is 6 and y is 6. It is always good practice to verify our final answers mathematically. We will plug these numerical values back into both original equations. The first original equation given to us was x plus y equals 12. We substitute 6 for the variable x and 6 for the variable y. The left side of the equation becomes the simple sum of 6 plus 6. Adding 6 and 6 together yields a total sum of 12. This calculated sum of 12 perfectly matches the right side of the equation. Our proposed solution successfully satisfies the first required condition. Now we must check our solution against the second original equation. The second equation given was x multiplied by y equals 36. Once again, we substitute 6 for x and 6 for y. The left side becomes the product of 6 multiplied by 6. Multiplying these two numbers yields exactly 36. This product perfectly matches the right side of the second equation. Our solution successfully satisfies the second required condition as well. Both equations are completely balanced with these specific values. This mathematical confirmation proves our algebraic work was flawless. Thank you for watching this detailed step-by-step solution. Please remember to like the video and subscribe to the channel.